And it's recording. Let's start the share. All right. Sorry for the delay there. I don't know exactly what's going on. I'll have to do some troubleshooting. That was a surprise that that was crashing on me there. So, what we're gonna do today? Let me get my chat working here. Carter, are you here?
Yes. Sorry
Cool.
about that. I'm right here.
No, it's fine. I just want to can you because I'm not gonna be able to keep an eye on the stream, so if you can keep an eye on that, that'd be sweet. And please feel free to interrupt me. And of course, anybody can jump in anytime if you have any questions here. But if you ask a question in the chat, Carter's gonna field it. If he can field it by text, he will. But he can also just interrupt me, or if you want to interrupt me, and just we can do that. Or if you whenever there's a meaningful breakpoint, we can do that. Okay. So let's talk about this announcements. So get clickers going. We're not going to do them today. We're gonna do a dry run practice run on how to do clickers today and how this is going to go down. I'm just going to go through this a couple of times, but you should be able to get those clickers going. I know that there's any if there's any questions on how that works. Basically, I can't do it from the student side, so I can't see it, so I can't demonstrate it. So this is kind of sucky. But once you go to iClicker.com, or I don't know what the actual, I think it's iClicker.com. If you can't find it, just look up iClicker. It's by Reef. And then you set up your portal, and then you basically look for the class. Has anybody set it up and found the class, found the class yet?
Yeah, I found the class, but I don't really see anything listed inside the class.
Yeah, because you won't see anything until I make Clicker go live. And so it'll look like it, but at least you can if you can find the class and see it, then that's all you need. That's where we need to be at this point. So that's perfect. So, and just to be also crystal clear, that physical clickers will not work with this one. You can only use the app for this version of this class because we're online. If you're in real life, you can use the physical clickers. But even still, if we're in real life, there's advantages to using the software clicker because it shows you like statistics and it actually gives you like analytics and that kind of stuff, which is pretty cool. So, the app is better, I think, a lot better than the actual physical clicker. There's always a little bit of drama that goes along with this, especially a class this large. So we're gonna try and hammer that stuff out. So what we're gonna do is we're not actually gonna use them today, but I want to show you how we're going to use them. In the next class, we're gonna try to use them, and then from there out, starting next week, we're expected to use them from there on. So cool. All right, we got a lot to get through, so let's get moving on here. So we want to basically kind of wrap up chapter 1 today. There's a lot of stuff it's not that many. Well, it's a lot of subjects right here, but inside of these, each of these can get really long. And what we're going to do is we're going to talk about this kind of in a spiral approach, meaning what we're going to do is we're going to take a look at this. We're going to talk about them briefly this one time in this lecture right here, but we're going to see these things come back a bunch throughout the course. We're going to revisit these subjects over and over and over as we spiral down, and we're going to hit these same subjects multiple times. So as we're going through this, if it feels like we're going really fast, it is because we're going really fast. But that's because what we're trying to do is just set the stage and create basically just a start for this, like an introduction to this. And I know, and I apologize, I know I'm going really fast, but the cool thing is the book is really good. Has there been any drama around the book? You guys picked it up? I think somebody posted it, but maybe they posted it also in the I've not been on the Discord, but did anybody find a maybe not so legal version of it? Does anybody have a PDF of it that been going around?
Some people are actually asking what the class ID for the clickers are too.
It's just I think it's MUSC 1800. I think that's what we're using for the class ID. Cool.
What I did is I went to University of Colorado Denver, and then it said like what class is it, and I looked up acoustics and I found it. So
thank you. Yeah, because I can't do it from my side, so like that's helpful. Cool. All right. So So just on that note though, has anybody found the book at all? Like a PDF version of it for now?
We dropped the link to the PDF in the chat because I saw some people did have it.
Okay. I still think, like I'm a big believer in actually owning this book. This is a book that's worth having on your bookshelf. Whether it's physical or Kindle version of it. But I would say that in the meantime, so if you're waiting on your order from your book, check out the PDF of it for now, because that should get you through it for now. But like I said, get the real version of it because it's awesome. It's a great book. You'll want this thing all the time. And having it in Kindle library, it's pretty cool because you can just read it anywhere and it lives in the cloud. So, okay, there's a couple things that we didn't get to last time that I want to go over because and I know that we're probably going to get pushed back a little bit today because we have a lot to get through. But was this idea of, and we're going to start adding this in. And what I want to do is just introduce a couple concepts here. So we were talking about the nature of sound, and we're just talking about how sound, moves around through the medium. And as I mentioned before, one of the important things to note and kind of remember is that all sounds pass through the medium at the same rate. Actually, all waves pass through the mediums at the same rate. And so this isn't necessarily a property of sound, it's a property of waves. That the medium stays the same place, but the energy passes through the medium, and it passes through at a constant rate. Now that rate can change based off of if you change something fundamental about it. Say like when we were talking about the mass spring, it's like I can change the tension of the spring or change the weight, or the pendulum. I can change the length of the string, or I can change the weight of the mass of the weight on there. But like how that correlates to sound is all the sound is going to pass through the sound through the air at the same rate unless we change something fundamental. So in other words, like temperature. So we're going to talk about temperature in a little bit, but temperature, when we talk about it, temperature raises the speed of sound, and cooling it lowers the speed of sound, but we'll get that to a minute. So the first concept I want to bring to light here is this notion of what we call velocity. So velocity is distance over time. And so when we think about like you're driving your car, we also call that speed, but and I'll denote the difference between speed and velocity here in just a moment. But when we talk about velocity, is how far you went over over a period of time. So if we talk about meters per second, miles per hour, all these are can be given in terms of velocity. Now, the important thing here, I guess, to determine here is the velocity is a physical, in physics, we use velocity. That means it has both a rate and a direction. So velocity can be forward or it can be backwards, or it can actually be in any direction. But we talk about velocity as being it includes a direction. So when we talk about sound, sound only moves in one direction. So really what we do is we call it the speed of sound. But in this case, we talk about this term of velocity. So in this class, I'm going to use velocity and speed interchangeably. In true physics, that's a no-no. Speed and velocity are different. But in this class, just because of the nature of the way sound works, sound travels. I mean, you could say that after it reflects, it has a negative velocity because it's going in the opposite direction. But for the sake of what we're talking about in this class, we're going to use the terms velocity and speed interchangeably. But again, in physics, in true hardcore physics terms, those are two different things. But I'm going to use V when I mean speed. So because we're talking about the speed of sound. So in this case, we have velocity equals distance over time. And we can go through and we can actually put some of this stuff to work for us. So let's talk about the speed of sound for a minute here. So the speed of sound, it is, and this is what I want this one to burn in your brain. This picture, by the way, is kind of cool. It's this is a picture of a jet breaking the sound barrier, and this is what ends up happening is as the plane is approaching the sound barrier, all the sound energy gets compressed in front of the plane, and as it passes through, it creates this vapor cloud. And so it kind of gives it this cone. It's a really flash. It's a blast. It goes boom. It's really quick. And when a plane passes through, when it creates the sonic boom. And what I also think is what's interesting lately, if you watch any of the Marvel show, well, actually not just Marvel. If you watch any of the superhero movies that are happening lately, things like actually even it was shown in the last Wonder Woman, terrible movie, but they showed it in the last Wonder Woman. But I think it really shows up in Superman a lot. Superman, when he flies around, he actually breaks the sound barrier a bunch. And he actually does this. If you watch very closely, when he breaks the sound barrier, they do this in the movie. You'll see this little puff of air as he passes through it, and it's one of those little subtle, tiny things that they throw in the movie, but it's pretty cool. So I said here the speed of sound. So and you see I have a little asterisk here. It says at 20 degrees C at sea level. So pressure and temperature do affect this, but this is what I want. This is what I call 3 a.m. knowledge. I want this number burned into your brain for the rest of your life, so that if I were to call you at 3 a.m. and I'm like, hey Joe, what's the speed of sound? It's 344 meters per second. Go to bed. Shut up. So basically, I want this to be burned into your brain for the rest of your life. Like, this is just part of this. This should be burned in there. So I'm going to give this to you in 344 meters per second, but it also could be described as 1130 feet per second. Now, when I went through this stuff, I learned it as 343 meters per second, and it was 1126 feet per second. But it's, like I said, it's a little bit variable. So we're gonna stick with this number right here. So 344 meters per second or 1130 feet per second. Is going to be what we call the speed of sound. So the speed of sound from here on. Yeah, totally agree, Haley. That the only good part was the Linda Carter cameo, which, by the way, is funny because I was watching on HBO Max, and so while we were getting ready to watch that, we were like, "Oh, let's go watch the old Wonder Woman, the Linda Carter Wonder Woman, the original ones." Which those are what were showing when I was a kid. So I remember like watching those old Wonder Womans, and it was hilarious to watch those old Wonder Womans as an adult because you're like, oh man, I mean, it was what it was, but it's funny. It was a funny movie. Okay. Let's jump into our first question here, and let's work through some algebra, and let's work through this. Like, we're going to get our math gears turning here because some of us haven't had math for a while, and it may not be, and it may be just a little bit unfamiliar. So we're going to walk through this kind of as a group together for a couple times, and then we're going to start working through the math on our own. Okay, so we see this classic one right here. You see lightning flash and then hear thunder 3 seconds later. So the important question is, should you be worried? But the answer to this is, well, we got to figure out how far away this lightning is. So the classic one that we always think about is that like we're sitting there in a summer storm watching the lightning. We sit in there and we think, oh, it's a mile per second, right? That's what we've been grow up like learning. But that is so not the truth, right? After just the number that I just showed you on the previous slide, we can see that that's not going to be quite the case. So if we see lightning flash, then hear thunder 3 seconds later, should you be worried? So to determine that, we have to figure out how far away we are. So let's start with velocity equals distance over time. So what we know is that in this case, what we're doing is we're solving for, well, we know what the velocity is because it's the speed of sound, because it's, I guess we should step back for a second and talk about this. We can consider light to be, well, light moves at the speed of light. That's really fast. It's like this fast. It's like super fast, right? No, like light moves ridiculously fast. And for all intents and purposes, light moves at, we'll say it's instantaneous. Whereas the speed of sound is a lot slower. So when we see lightning happen far away, we see the light hit us really quick, and then we hear the thunder as it approaches us sometime later. And given that discrepancy, we can determine how far away that is. So again, we're like, in truth, it takes time for the light to get to us, but in the grand scheme of things, that's so fast that it's not really that important for what we're discussing here in terms of like human scale. But the speed of sound really is a lot slower than the speed of light. So we're going to consider that instantaneous, and then we're going to look for the delay. So in this case, what we're going to do is we know the velocity of sound is 344 meters per second. We know that the distance is what we're trying to determine, and we know that the time is 3 seconds. So doing a little bit of quick algebra here, and I'm not showing it explicitly on the screen right here, in case it's been a while since you've had the algebra, what I'm doing is I'm multiplying both sides by time. Because this time is in the denominator, if I multiply this side and by this side, and with an equation, you can do whatever you want as long as you do it to both sides. That's what an equal sign is. If I want to multiply this side by 100, I can multiply this side by 100. So it just doesn't, so no matter what I do to one side of the equation, I have to do it to the other. So in this case, what I'm going to do is I'm going to multiply both sides by time. And in doing so, the denominator and the numerator of time cancel each other out, and I'm left with d. So I'm left with d equal, or v times t equals d, which is what I wrote here. I just flipped it over. And with an equation, you can flip them both over in different direction right here. So what we're going to do here is d equals v times t. And let's actually substitute the numbers in now. So d equals 344 meters per second times 3 seconds. And again, this is in the numerator and this is in the denominator. So the seconds therefore cancel each other out, and I'm left with 3 times 344. And the result is 1,032 meters. So this flies in the face of what our intuition, or what we've been grown up telling us, that 3 miles is 3 seconds is 3 miles, and that is so not the case. It's 1 kilometer. That is a lot closer than 3 miles. 3 miles, I'd say, yeah, you're actually probably pretty safe. 3 seconds, I mean, 1 kilometer is not that far. It's 1,000 meters. So should you be worried? Well, depends on your situation right there. Now, you'll notice that I'm doing this in meters, and that's because I want to get on with the rest of the world. I'm teaching this class from a physics perspective, and in sciences, we only use the metric system, or what we actually call, it's called the International System of Units, or what we call the SI system. So you'll hear this term called SI, and it stands for, it's French, so System International or something like that. I'm not exactly sure what it is, but it's what we here in America call the metric system. It's what everyone else in the world calls measurement, right? So we're the weird ones here in America. And I've been a scientist for most of my career, most of my life, and so I'm hell bent on working in the SI system. I only work in SI. I don't use like imperial systems. The imperial system is stupid. I'll just say that right now. I'm going to go out on a branch. It's stupid. There's reasons to use it, but I guess as kind of a weird side hobby, I do like investigate a little bit about why we use certain measurement and how we use measurement systems and why we use different measurement systems. And, well, to the point here, like basically there's a lot of good reasons to use the metric system. There's a couple good reasons to use the imperial system, but for the most part, it sucks. It's lame. Like I do a lot of, I would say, fabrication, construction, materials work and stuff. And I'm constantly, or even cooking, like when you have to do like, it's 4 quarts to a gallon and like how many cups are in a gallon? That is such a pain in the butt, like to figure that out. And like these stupid old measurement systems just don't make any sense. So what I'm going to do here is I'm going to be teaching this class exclusively in the SI system, as any science class would be done, but as I would say, as any class should be done. So, so in this graph right here, or in this plot right here, there are 3 different countries on the planet Earth that don't use the metric system, and they're highlighted in gray. So I guess what I say, the regions in gray are the areas that don't use the metric system. Does anybody know what they are? Don't Google it. See if you can see it. Well, we obviously got the US right there, right? Can anybody identify the 2 other countries on the planet that don't use the metric system?
Liberia, Burma, Myanmar, and
Yep.
the US.
Yep. So here's Liberia right here, this little tiny West African country right here. And that was because Liberia was formed as a country of freed American slaves that returned back to Africa from America, and they dragged our stupid ass system with them. So I feel for them in terms of their like, I don't know why they're stuck on that system. And then we have Myanmar or Burma over here that they're using the imperial. And I'm guessing that was probably because it was like an English colony at one point. You know, the English were the ones who kind of spread this around the world, but even England isn't on this system. Even though, like, if you talk to a British person, they will understand what you might mean by miles and by pounds, not the money, but the actual force of pounds. So, but in truth, well, they use other crazy ones like stones and some of these other ones too. But officially they're on the metric system here. So I have also noticed that, like, in talk of Corona a lot lately, that we see that they talk about it a lot, that our proportion of our COVID cases to our number of people that we have on the planet. They tout it as, I've always thought it was 5%, but they said, like on the news, they say America is 4% of the world population. That means that 96% of the rest of the world's people use the metric system. Only 4% of us do it. That means that's just stupid. Let's get with the program, people. Like we need to get on board with the rest of the world. Like it's like 4% of us are like, nope, we do this, and every mechanic on the planet has to buy 2 sets of tools now, so that you have to do this. So anyway, I'm going to be using this term, and I'm going to really try to convince you to think in terms of metric. So in this class, we're only going to be using 344 meters per second, with a couple exceptions. I live in the U.S., and there are some interesting cases where it's a good idea to also talk about it in feet per second. So I will talk about that on occasion, but for the most part, I work completely metric. So like on my phone, I have it completely like turn your phone weather app to Celsius, and it gets confusing at first. You're like, oh, it feels weird to like figure out what the temperature is, but it takes like a couple weeks, and then you get the hang of it. Because like I got into it with a friend who's like, he's like, yeah, but you get more resolution with Fahrenheit than you do with Celsius. Bull crap. All you got to do is add a decimal point in there, and you got double the resolution. And so like, and truth is, I don't care. Do I care if it's 20 or 21 degrees outside, or do I care if it's 13 or 14 degrees outside? No, I care if it's, do I need to wear a jacket, or is it flip-flop weather? Like, and that I need a range. So in terms of human temperature, not that big a deal. So you're going to be seeing me use this a lot lately. This is my little soapbox for the day. But like, it's just crazy. It just baffles my mind that we're stuck on this stupid system. Or like we're talking about, what was I talking? We were doing some measure. We were cooking the other day, and we're talking about in terms of ounces. You're like, wait, is that fluid ounces or is that the weight? How stupid is it that we have ounces that describe how much a liquid volume, and also that it describes a weight, and the two are different than one another, but we have the same name for the two of them. Ugh. All right, enough of that. What's up?
Do you think that it's like it's actually possible for like the US to make that change, or do you think we have so many different things in place already using that system?
It's pretty fascinating. We actually tried. So technically, we are actually on the metric system, but we don't use it. Or they tried to make a push, but what they did is in the 80s, it was like an early 80s thing. They tried to make the switch, but the government goes, "We're gonna make the switch," but then they pulled back and they're like, "But we're gonna make it optional." And then nobody did it. And then every other country, they're like, we're gonna make the switch, and we're gonna make you do it, so that all labeling must now be done in this form right here. And the US, they're like, you can decide if you want to do that. And everyone's like, well, I don't want to change anything, so we'll stick with it. So I don't know, but this is why space shows, this is why satellites blow up. I just listened to this funny book called Humble Pie. If anybody's read it, it's about math mistakes, famous math mistakes and engineering mistakes. It's corny, I know, but it was interesting. They talk a lot about how much this causes like engineering disasters. This one
various space things, like thought like space crashes were caused by conversion errors.
Exactly. We've had a number of things blow up and crash into each other and stuff because of these conversion things, right? Exactly. And also just decimal point like things. It's really easy. Yeah, if you've not read it, the Humble Pie book is pretty interesting. It's kind of fun. It's a quick read. I just did it as an audiobook, and it was suggested by Wired. It was a Wired Best of 2020 book. It's written by this Aussie who lives in London, and it's just basically funny math things, but it talks a lot about math errors. It talks a lot about computer errors and stuff like that too. Pretty fascinating stuff. So anyway, that's my thing. So it drives people nuts who work with me in construction, because I only work in metric. And I live in the US, so I do studs 16 inches on center. I work with 4 foot by 8 foot sheets of goods with drywall and with panels and all that kind of stuff. So of course I do that, but all my tape measures are metric. And so anytime anybody comes over to my house, it drives them nuts, especially my wife. She gets like so annoyed with my tape measures, because I have like all tape measures. I have a few Imperial ones in there, but I use almost all metric tape measures. And it just like, everyone looks for it, and like people open it, you can see their face go like, it just doesn't compute. But it's just a measurement. It doesn't really matter. So, all right, cool. Let's move on. Okay. So let's talk about this in terms of sound. And so we're gonna get our algebra brains going here. So one of the most important concepts in this is we talk about this notion of wavelength and frequency. So when we talk about something, we talked about this last class a little bit, and we're gonna drill way down into this notion of wavelength and frequency. But wavelength is how long a wave is in a medium, and we're gonna 99.9% of the time in this class, we're going to talk about sound in air. You can talk about sound in water and sound in solids and all this kind of stuff, but we're going to talk about, when I say like wavelength, I generally mean sound of the length of a wave of sound in air. And then we have this term, what we call frequency. So frequency is going to be how frequency, that one wavelength, when we talk about something being periodic or cyclical, something that repeats itself over and over, it's going to be passing by us. And as it passes by us, we're going to say what rate is that passing by us. And so that rate can be determined in terms of how many times per second does this go by. And so what we're going to look at here is we're going to look at, we're just going to look at this wave for a second right here. And we have the length of this wave right here. So this is what we call, I guess this is an important concept here, is what we call amplitude. So amplitude is the distance from, it's like, we look at our displacement. We were talking about our displacement last class. Our displacement goes from our resting position to our maximum displacement. And we can imagine if we want to imagine what this is showing us right here, that this could either be a transverse or a longitudinal wave. But we're going to assume that if this is talking about sound, that this is going to be a compression wave. And what this is compressed. This is where the air gets squished together, and this is where the air gets stretched apart. And so these are the displacement, how far the displacement of our air molecules are getting squished and pulled from each other. This is going to be a completely still room. This is going to be when they're squished together, and then this is going to be when they're pulled all the way apart. And so we have our wavelength, and then we of course have our wavelength. And our wavelength is this thing, as this thing is hauling by at 344 meters per second. We can see that the length of the wave is going to be given by this right here. This still may be a little bit foreign, but we're gonna keep talking about it for a long time. But I want to bring into this one equation, and this one equation is the most important equation for the entire rest of the semester. So I want this one burned into your brain as well. Da da da. V equals F times lambda. So what we're going to do is we're going to start combining some of these concepts in here. So velocity is the frequency, and then we have our Greek symbol called the lambda right here. It's a small lambda in the Greek symbol. And what that is this means wavelength. So what we can see here is velocity. And if we do like a quick dimensional analysis, meaning if we pull apart and we look at what what these are. So velocity, if you remember, is given in distance by time, meters per second, or something along those lines. So we'll just say meters per second for right now. So it could be miles per hour too, though, or it could be meters per hour, or millimeters per minute, or it could be any kind of these things. But we're gonna say it's meters per second. So if this is a meters on the top and seconds on the bottom, if we look at this one right here, this one has frequency, which is per second, and a wavelength is a length, which is given in meters. This is meters per second. Cool. So this is basically given in per second, and this is in meters, and this is in meters per second. So therefore, what this means here is that velocity equals frequency times wavelength. Now, this is an easy way we write this, and this is why we write this way here, but this is not how we typically use this equation. The reason I write this one right here is V equals F times lambda, because I'm going to refer to this a lot through this whole semester right here. But like I said, in practice, usually we know what this number is, and we're solving for one of these two right here. So, but it's really hard to remember if I put F over here, which is the V on the top or V on the bottom right here. So this is the easy one to remember. And then what we do is we do a quick algebra to switch over and go to the others, to go to the other versions of it and solve for wavelength or solve for frequency. But the cool thing here is that if we know if we know one particular attribute, if I know the frequency, I can figure out the wavelength. If I know the wavelength, I can figure out the frequency, because like I said, for the most part, we're going to say that, the velocity is constant. It's 344 meters per second. I will say that, I'll reiterate this one more time, that as temperature goes up, the speed of sound goes up. And as temperature goes down, the speed of sound goes down. And that's because if we think about what heat is, it's just vibrating molecules, air molecules. Heat is just is how fast they're vibrating. And if it's cold, they don't vibrate very much. And there's all these kind of crazy physics experiments going on to try to get the coldest temperatures in the universe. Like there's no, 0 Kelvin. So 0 Kelvin is where there's absolutely no energy. So where they're completely frozen. And we can get pretty close to it doing all sorts of crazy tricks in chemistry and physics. But, we're not there yet. But all other time, that if we talk about just like in real world, air temperature is just vibrating air molecules right there. And the hotter they are, the more they're vibrating. And the reason is that simplified reason of why that the sound speeds up in hotter air is that when those air molecules are vibrating back and forth and the sound wave pushes on it, the vibration transfers its energy. Because they're vibrating so fast, the energy gets transferred to its partner or to its neighbor a lot faster. And if it gets pulled, it gets pulled. And if these air molecules are moving very slow, that if it goes push, and it's going to move it along slower. So the correlation, and we can do a lot of different math if we wanted to, and I'm not going to go down that in this class. I do think it's kind of interesting math, but understanding, you could do the math if I wanted to go to, if I raise the temperature, how fast it's going to change the temperature. But again, it's not really that important for most of what we do in this class. But, if you're doing like a show outside, like a concert outside in the winter versus the summer, it may have some influence on some of your sound system setup. For the most part, when we talk about like acoustics, like indoor acoustics, we tend to work in normal kind of like room temperature environments. So it's really not going to change our numbers that much in the real world. But like in the actual world, it does. Outside of the rooms, it does change a little bit. Okay, back to the question. Back to the task at hand here. Let's put this question to work for us here for a second. Let's do some math. So what is the wavelength of a 20 hertz sound wave? We haven't talked about the terms of the range of human perception, but what we can say is that the human perception, the range of human perception of sounds goes from 20 hertz to 20,000 hertz. So what we're going to do here is we're going to solve for the wavelength of the lowest frequency of sound that we can hear. And I would go so far as to argue that you probably can't hear this. 20 hertz is really, really low. You can perceive it, but it's usually going to be because something's vibrating in the room. You can feel it more than like in your chest and stuff, but hearing 20 hertz is pretty hard. It's just a nice convenient number that we use, but honestly, most of us can't hear 20 hertz very well. But what I want to do here is so what I'm asking us to do is solve for the lowest frequency or the wavelength of the lowest frequency that we can hear. And if you're pretty math proficient, I want you to try and beat me to the answer here on a piece of paper if you got one around. So for this class, like I said, you don't really need to take a lot of notes because I'm going to be putting everything up and I want you listening to me and engaging and not furiously writing as many notes down. Everything I'm talking about is going to be in the book. Well, most of the stuff is in the book. But I have all the slides recorded, slides posted and videos recorded so that you can always refer back to it. You may, if you're taking notes, and there's nothing wrong with taking notes, but you may want to just do a little thing here or there, a little note here and there of things that you're thinking. But also having the ability to have a piece of paper, a pencil and paper so that you can actually do the math is going to be really helpful and really important. So just having, if you're typing like on a tablet or on a keyboard or something like that, it's a lot harder to do this math. So having a pencil and paper because of the math will make this a little bit easier. So like I said, if you can beat me to the answer here, go for it. But I'm going to walk you through this here, and then we're going to walk through and we're going to do some questions together. So what I'm going to do is I'm going to start with the same thing I did before, V equals F times lambda. And then the next order of operations. So this is exactly how I would write this down on a piece of paper. V equals F times lambda. Let's start with that. And then what I'm going to do is I'm asking for the wavelength. So I'm solving for this lambda right here. So what I'm going to do is I'm going to divide both sides by frequency. And so because I divide this by frequency, the frequencies cancel out. And then the V equals over F over here, and then all I did is I flipped them around. I don't have to do it that way, but I did it kind of in two steps. So I divided by frequency and solved for, and flipped the order around. So I'll have my iPad out next time so that I can switch back and forth and actually be able to do the math by hand, but I don't have my iPad. It's actually being used right now, so I can't really do this. I'll do this more so you can actually do it by hand. But lambda over F, or sorry, V over F equals lambda. So lambda equals V over F, and let's put some numbers in there. So it's 344 meters per second divided by 20. And because it seems kind of strange to think about this, but this is hertz is also per second. So it's a little strange to think about these canceling each other out right here. But if we think about what this is a per second in the numerator and a per second in the denominator over here. And so that this hertz and this second cancel each other out, and we're left with just a meter right here. So the answer becomes, therefore, 344 meters per second is 17.2 meters. So think about that for a moment here. And again, I'm asking you to think in terms of metric. But if you want to do a quick conversion, you could roughly use like 3 feet per meter right here. So if you're, and then just doing back, off the top of your head calculation right here, if we did this as something like 17, or if you did it as 20 meters, as 20 feet, just roughly speaking, and 20 times is going to be like 60. So it's going to be less than 60 feet for this sort of thing. So 60 feet. Is 60 feet big or small? Well, depends on, the term big is relative, right? So is 20 feet big relative to the Empire State Building? Nah, it's tiny. But is 20 feet big relative to you? Yeah. Oh, sorry, 60 feet. Well, okay, I'm gonna stick with meters here. So I would just, if you want to mentally picture 60 feet, you can do that. And actually, it's a little bit less. If somebody wants to do that in feet, what's 1130 divided by 20? Yeah, it's not quite 60. It's 50 something or other. But I'm going to talk about this in terms of 17 meters. So 17 meters, 17.2 meters, large or small? Well, relative to, like I said, relative to the Empire State Building, it's going to be small. but relative to me, it's going to be large. And this is kind of this is where the interesting part of acoustics starts to creep in. The point is that you can visualize 17.2 meters. Like if you were to just, like, you can put that on a string. It's not like the size of planet Earth, and it's not the size of an ant. It's not the size of an angstrom or a nanometer. It's actually something that interacts with our real world. And this is why acoustics is fascinating, because these wavelengths are actually relative. They show that these wavelengths, these sounds and air actually are realistic world, like sizes. The size of these things are something that we interact with. It's like, again, it's not the size of a galaxy. It's not the size of an atom. It's the size of stuff that we deal with in real life. And that is why acoustics is interesting, because these sounds interact with the real world with us all around here. So it's all over the place. So that's what's interesting. So what I want to do here is I want to look at this one right here. So this is the lowest frequency we can hear. The wavelength is 17.2 meters. Well, let's do it again, but let's do it on the scale of the highest frequency that we can hear. So what's the highest wavelength of 20,000 hertz sound wave? So beat me to the answer. Go for it. Try and write this down. Try and beat me to the answer doing exactly the same thing we just did, but now you're going to do it with 20,000 hertz instead of 20 hertz. And so the term what we use here is 20,000 hertz can also be written as 20 kilohertz. So this kilo means there's 3 zeros right here. So sometimes when I say 20 kilohertz, what I mean is 20,000 hertz. And for this equation to work, you have to use this version of it right here, because I'm not giving it in terms of kilometers. You could do kilometers and kilohertz, but I'm looking at hertz and meters. So here we go. Beat me to it. Try and fly through this. If you're still kind of grinding on this, like, we'll walk through this stuff together. So V equals F times lambda. We solve for lambda. So lambda, we divided both sides by F to get lambda equals V over F. And then what I'm going to do is 344 meters per second divided by 20,000 hertz. And again, because this is per second and this is per second, cycles per second, that this cancels out. And what we left with is 0.0172 meters. So again, if you want to do this in feet, you could, but the problem is now you're trying to compare a decimal foot. I hate feet in inches. Like I hate fractions of an inch. I do a lot of woodworking and trying to add 5/16 times 7/30 seconds. I have 3 7/30 seconds and I need to add 5/16 to that. Like, the math on fractions blows. So, and I understand why what are 3/16? I understand why the 16th came about, because when we had pretty crude measurement systems. We just kept dividing things by 2 and half and half and half and half and half and half. But the problem is that it's just a pain. So then we're dealing with like what is like 1.42 inches? You're like, well, on a ruler that I can't do that. 1.42 inches. Usually, what ends up happening is you're like, well, that's just underneath 1.5. You're like, no. If you do joinery and cabinetry, or like I build speakers, I need sub-millimeter accuracy. I can't fudge these numbers, and so that's crazy. Or my friend who works in he's a civil engineer, and he works in feet and decimal feet. So he works at 3.15 feet. So what's 0.15 feet? I don't know. Like that's so confusing. Like it's so confusing to work. So then I have to take 1.15 feet and multiply by 12 to get inches. But then I have to multiply the inches, any decimals on there to get, and then trying to figure out the fractions of that. Ugh, bleh, yuck. But here, this one's pretty easy. Here's where metric works well for us. So 0.00172 meters. Well, if you're familiar with this, or if you're one of our didn't grow up in the U.S. students, like you're in luck, because you'll be able to do this on your hand. In fact, like I want you to try and do this. Can you do 0.172 meters with your fingers? Can you show how big this is with your fingers? Well, it turns out, I mean, if you're comfortable with this, we can convert this to centimeters pretty quick. So in other words, we just move this decimal point 2 times this way, and we're talking in terms of centimeters. And if you're familiar with centimeters, that's a pretty easy value to think about. Centimeter is about yay big. And so I'm talking about 2 centimeters. So that's 2 centimeters, right? About 1.72 centimeters, more or less, right there. And that's that right there, my friends. That is 20,000 hertz. That's the highest frequency that's the wavelength of the highest frequency that you can hear. So the wavelength of sound and air, to be explicit. So this means that the range of human hearing, the wavelength of range of human hearing goes from 1.72 centimeters to 17.2 meters. Cool. I don't know. I think that's pretty badass. So, so basically we can go, this is the highest frequency that we can hear right there. The wavelength of the highest frequency we can hear. But once again, it's not like some invisible number. It's not like the size of a galaxy or the size of a planet or the size of some inconceivably small value or some inconceivably large value. And I think this is neat because we can't see sound, right? It's invisible. It's just moving air that's wiggling air that's going back and forth. But what this does is it shows us that the scale of these things interacts with our real world. And it's something that we can start to do it. So when I walk into a room as an acoustician, I think about the wavelength relative, and that's a big key part of this, the wavelength of the sound relative to the objects or the room. That's what, well, I won't say that's what acoustics is, but that's a very, very large part of understanding acoustics is. So because I've been doing this for a long time, I have a pretty intuitive sense of how big a wavelength of sound and air is. You're going to be doing a lot of that this semester. So here's how this is going to go. So what we're going to do this again, we're going to do this one more time. But here's how we're going to do this. We're not going to do this as a quiz question today, but we're going to pretend it is. We're not going to do that. We're going to do this as we're not going to do clickers, but we're going to pretend it's clickers. So what we're going to do over here is I'm going to go, what is the wavelength of a 1000 hertz sound wave in air? So normally at this point, I would hit go and I would, let's see, I would go through and have you click in on this. But the way we're going to do this is I'm going to practice this one time. I'm going to only do this one time for class today because we don't have a ton of time. But what I'm going to do is I'm going to create breakout rooms here. And what I'm going to do is I want you to come up with your answer right now. So 1000 hertz, come up with an answer. Don't type it in the chat, please. Because I want you to I'm going to ask you to refrain from typing the answer in the chat. But what I'm going to do is I'm going to send you, I want you to look at this for a moment, do the math. And what I'm going to do is, let's go down to, I want you to try and figure out the answer here and see what you get. And what we're going to do is I want you to confirm with your neighbors, your virtual neighbors, if you got the right answer. And if you didn't get the right answer, I want you to be able to dig in and figure out what the answer is. And if you're really confused, you can ask for help from your neighbors. If you really know what you're doing, you can offer help. But what I want you to do is when I push you into these breakout rooms, and I'm going to give you 2 minutes to do this. You're only going to have 2 minutes. This is a really short one. This is a test. So I want you to go into the breakout rooms for 2 minutes. Just go, did you guys get this answer? Did you guys get this answer? Yes, 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 yes. Are we all consensus? Did we get consensus? And if you have consensus, I want you to leave the breakout room and come back to the main room. If you're working, you can work through it and ask each other, try and figure it out. But it's only going to be 2 minutes long. So here we go. Try this up. Recreate. Cool. Go for it. Is it working?
So Merkel, I have a question for you.
So
So it is going to be a good idea to have a calculator on hand for this class then?
yeah, but you can use your yeah, it's gonna be tough because you can use your phone. You don't need a physical like a real calculator. Just use your computer calculator is just fine.
Okay. Yeah, because I have a graphing calculator that I like bought in high school that I've just been using.
Yeah.
So I'll
I mean,
just,
there's so much merit in still having just a classic calculator around. I have one too, and like I use it. I have it in my shop, and I use it a lot. So
gotcha.
yeah, and you spent the money on the thing, so you might as well try. You put that thing to work, and it's
Yeah,
quick. If you're
exactly.
fast with it and you know it, you then go for it.
Yeah,
But for-
it's a lot faster than using my phone.
Exactly. Yeah.
So,
And
okay.
especially like when you start learning, we're going to be doing some logarithms and exponents and that kind of stuff too. It's kind of useful to have an actual calculator for that sort of stuff. So good question.
Gotcha. All right. Cool. Thank you.
All right, close all these rooms. Get everybody back. Whoops. Okay. Well, hopefully everybody is back. I can't tell how many people are in there. Sorry, I don't have a timer on that. I thought I had a timer on the breakout rooms. I have to do. I'm still learning this one.
No, there was a timer that was going.
Yeah, for you, but not for me. I couldn't see it. So, well, maybe there is a way to set it up. I don't know. I haven't figured it out yet. This is the first time I've ever done breakout rooms. And normally I hate doing the breakout room thing. But what we're going to be using the breakout rooms for is just go in, to double check with everybody. And I'll give you something like, depending on how hard the question is, I'm going to give you a couple, a minute. So the cool thing is here is like, even if you're really confused and you don't have a hard time with this, rely on your neighbors. And it's going to be different every single time. Well, for basically what's going to go is for that day, all your group is going to be all the same. But for each time you go back in there, each day, it's going to be different people that when we set these up. So, okay. Cool. What did we get? What was the answer?
C.
0.343 meters per second. Yeah.
Wasn't it supposed to be 344? Yeah.
Oh yeah, sorry. So when I wrote, I'm sorry. Like when I originally did this class, like the way I came up learning it was 343, and so when I started when I switched to this book, because all my old textbook that I used to use was 343. So some of these ideas I still in my brain when I write these up, I write them as 343. So it's close enough for this one. So I apologize. It should be 344. I'll try and make note of that and change that. So it's 343 meter or 0.343. So if we want to figure that out, that's 34 centimeters or 0.3. It's a third of a meter about. So it's about yay big right there. That's about 34 centimeters right there. So, well, it's hard to tell because I'm like, depending on where I put it on the camera, right? It varies. But 34 centimeters, that's something that we can envision. So what they're saying there is 1,000 hertz, a middle tone, kind of in the middle of our spectrum, is going to be 343, is going to be 34 centimeters there. So that's something we can imagine. So that's 1,000 hertz. Cool. So now we've kind of gone on both sides of the spectrum there. So what did I do there? Oh, I accidentally doubled the slide up. My bad. What am I doing here? Did I copy this page like way too many times or something? Okay. Let's go back the other direction with it. So in this case, what I'm going to do is I'm going to ask you to solve. So we're going to go opposite. Instead of giving you the frequency and solving for the wavelength, I'm going to give you the wavelength and then I'm going to solve for the frequency. So it's exactly the same methodology. You just replace the F and the lambda from one another. So what frequency corresponds to 0.8 meters of sound in air? So what you're going to do, so write that down, 0.8 meters is the wavelength. So lambda equals 0.8. And what you want to do is you want to find, so V equals F times lambda, and then you want to solve for, we know the V and we know the lambda, but now you want to solve for F. So write that down. I'm going to push you into the rooms right there. Open all rooms. And hop in there, and I'll give you like a minute to try and figure that out, just to make sure that it works. I'll give you a couple minutes. So hop into your rooms. All right. We're all back now. What's the answer? What'd you guys get?
E.
430.
All right. Very well. Nice. So what we're saying there is 430 hertz corresponds to 0.8 meters. And once again, the thing I'm trying to really pound in here and trying to drill in is this concept of like that there's a relationship between the wavelength and the frequency. It's a really useful tool to be able to like kind of, well, now you know how to do the math. And we're going to be doing this math a lot, and especially in different variations of it throughout the semester. This is what I'm going to be calling the wave equation. If you work in physics, this is not the wave equation. There is such thing as called the wave equation, but this is a wave equation. So I'm going to call this the wave equation for this class. But like, you know, technically, if there's actually like there's a thing called the wave equation. So just real quick, I need some feedback here. Did that breakout thing work? Did it was it helpful or was it annoying? This is a new experiment for me.
Nobody in mine said anything.
Oh, really? Okay. So y'all need to so here's what I want to have happen is I want you to go in and go, hey, does everybody agree? You guys can talk on the mics or just chat in your break room if you want to as well. But just like confirm, did we all get the same answer? And if you didn't get the same answer, then work on it. How about give me some more feedback. Did it work?
On my I thought it worked well.
Pro, it took like 45 seconds to even get into the room. So
okay, how come it took so that's what this is class, like, and this is part of the engagement or this thing. You're gonna have to have clickers and you're gonna have to pay attention. So if you're surfing while you're doing this and looking and doing other stuff, this is gonna be a tough class to multitask with. It's important that you stay engaged. So when I hit go on this, but you know, we're building this up, this whole breakout room concept. So when I hit go to the breakout room, you're gonna have to be on it pretty snappy, be pretty quick. So that means like, you know, maybe if you're out going to the bathroom or something like that, you might miss the window right there. But for like other times, you're gonna have to be moving pretty quick here to get in, check with everybody, and get back out. Because I don't want to spend I want you to have the time to like talk to each other. And some of these I'm gonna give you some like maybe up to 5 minutes on some of these on these. And the hard part is I can hop into the breakout rooms, but for the most part, I can't see what's going on in there. So it's really tough for me to tell. Like when I do this in real life, the way that works in physical classes is you just look around and talk to your neighbors. Like, did you get C? Did you get C? Did you get C? Did you get C? And then oftentimes one person's going to be like, I have no idea what we're doing. And everyone's going to be like, okay, here's how you do it. Here's how I do it. Here's how I do it. Here's how I do it. And the other time, and I don't know, I haven't tried it. Can you share your screen in breakout rooms?
I think you can, only if you give us permission though.
Okay. I'll try to give everybody permission to do that. So that you should be able to, that if you guys want to share each other's screens, well, I don't know if you really need to for this one, like showing a piece of paper. I think the easiest way would be doing it on a piece of paper and holding it up to the camera. I know it's like ancient, but that's kind of the way to do it. But like basically, I want you guys to be able to like ask each other questions. So we're gonna be doing this a lot. So I guess I think it was Ethan that was saying there that like basically when I say go to your breakout rooms, get on it. Please be quick with it because I'm gonna be pulling you back out pretty quick. So, but I want a little more feedback as we go along here. If this works, if it doesn't, you know, this is an experiment on my end to see if this will work. But the cool thing is though, if you lean on your neighbors, you can get very good scores on these things because these are going to be scored. That said, with clickers, the way it's going to score is you're going to get 1 point for the right answer and 1 point for just guessing. So even if you get it wrong, you still get points just for guessing. So, but the annoying thing is if you don't show up for class, you're going to miss 2 points, well, per question. And that adds up. Getting zeros blows. So you're going to have to get that added up real quick. It also means if you're like multitasking while you're trying to like, I don't know, I've had students that were like, back in the day that were doing things like multitasking at work, and that makes it very difficult. This is a tough class. You're gonna have to be kind of focused on this one here. So cool. Cool. Thanks for pointing that out, Zach. So like I said, we're gonna mix it up. So you're gonna have different people every time. And I know that breakout rooms, like being forced, I hate doing breakout rooms when I do sessions like with like, you must discuss this, but I'm giving you a simple, fast one. Just confirm with everybody. Did you get A? Did you get A? Did you get A? Did you get A? Cool. How about, do you want more people per room or less people per room? I'm doing 3 to 4 right now.
Yeah, let's do.
I mean, I thought that was fine.
Okay. Because I will get worried if I do 5 or 6, it gets too many people in there.
I want to
So-
meet more people, so do more.
Okay. Well, we're switching it up every day. You're gonna meet new people in the other ones. So yeah, and I think also to that point, you're right. Meeting people when you hop into that room, do a quick intro. Hey, I'm so this is on the first time you meet in the class. Hey, I'm so and so. You only have like 2 minutes, so you got to be really fast. But hey, I'm Jeff, and like let's do this. So cool. And if you guys get through all the questions, you can either come back to the thing or you can say what's up and wait till you get forced out and say just talk. Say, what are you guys doing? What are you guys into? What music are you listening to? This class sucks. That kind of stuff. Cool. All right, let's move on. All right. So what we want to do here is, let's see what we're doing on time here. So it's 12:03. So I got about a tenth of the way of this content I wanted to get through for class today. So what we're going to do is we're going to push this back and we're going to keep working on chapter 2 for the rest of this week. So let's keep working on this, but I'm going to push decibels, the start of chapter 1. We're going to finish chapter 1 out through the rest of this week, and we're going to start chapter 2 next class. So this is going to change the syllabus up a little bit, but I think it's really important that we kind of drill these things in. And I feel like I'm even hauling ass, and we're still like behind schedule here. So, and I know I talk a lot and I talk fast. So, okay, let's move on here. So you're going to get really comfortable with that math, but I think, it's worthwhile. Also, just if you have some time, sit down and do some of this math. Choose a number between 20,000 hertz and choose between 20 and 20,000 hertz. Do the math. And then if you have a signal generator in your DAW, like Pro Tools, which you all have Pro Tools, I know you do. So pull up the signal generator in Pro Tools and play that tone. Go ahead and play a 430 hertz tone in Pro Tools, the signal generator, and to go, oh, that wavelength is 0.8 meters. It's really interesting. It's kind of cool to associate these kind of like weird like concepts of they feel like they're two different things. Like the physical world and the sound coming out of your speakers are two different things, but it's the same thing. Rad. Okay. So let's talk about this notion of let's move on a little bit. This notion of what we call complex waves. What we talked about last class was this notion of what we call simple harmonic motion. So simple harmonic motion is the creation of creates what we call a sine wave. So to go ahead and just define this thing is a complex wave is anything that's not a sine wave, right? So a complex wave is which is exactly what we use sine waves for testing and why they show distortion really well. So if I put the reason what I said right there was basically we use sine waves as test signals because if it distorts the wave, if anything comes out, if I put a sine wave into a piece of equipment and anything comes out but a sine wave, that means it distorted the signal. We can measure the distortion and the effects of that distortion. So when we talk about like guitar amps, or we talk about like microphones, or we talk about speakers themselves, speakers have distortion in them. That basically even though I want it to play a pure sine wave, a crappy speaker is going to play it with a lot of different harmonics built into it. So, but let's just say that I'll just define this out of the gates right now. A complex wave is anything that's not a sine wave. So let's look at some examples of this thing right here. So to do this, I'm going to switch over to Wavelab for a moment here. Let's bring it up. And where's my thing for today? Class 3 sound. Let's drag these in. I believe this will work. Oh, I was doing this in. Must have did this in. Let's see. That'll work for now. These are all 48, I hope. Cool. But let's just create a signal generator. Let's create a sine wave. 500 hertz. Sure. Level. Let's do it -6. -3 is fine. Let's do this at 48K. Okay. Let's start with that one. Actually, let's do a source. Let's do triangle, generate, and let's do a square, generate. And so let's start with our sine wave here. you can see that we have a sine wave right here. And what I'm going to do is I'm going to pull this up. I have two. I'm going to start this up. Let's see, log in. If you want to hear this, which is important, start transmission. I'm going to copy this to the chat. Please log into this one. Or click on that link. If I'm going to watch that. If you get blocked out because it's too full, because this is going to happen, I set up a second one. And what I'm going to do is, let's just do this as 0.2. And I'm going to copy this. This is for the one. If you couldn't get into that first one because it's full, log into this one. Please don't log in. If you log into the first one, don't log into the second one. That should cover us. Let's give this thing a listen here. I don't know. Just watch your ears in case this is loud. Working? Cool. Pretty boring. Well, maybe not too boring. So another thing that we wanted to do is start describing how this sounds. How would you describe that sound?
Flat.
Flat. Sure. Not in terms of musical flat, but just like boring flat. Yeah.
Yeah, just the most basic.
Yep, basic. We got a basic wave. What else? Give me some more descriptors. So what we're doing here is what's called timbre. So we're describing what the sound sounds like. And the weird part is in the English language, we don't have a lot of words that accurately describe sound. So a lot of times what we use is we use these other terms. Like we use the term warm, cold, like flat, right? Flat is how squished something is, like a physical description of how of something. Yet we're attributing that to how sound works. And so English is not very good at describing sound. So, but what we want to be able to do is start and this is what critical listening is, the class that I teach, is we describe, I want you to be able to describe very accurately using English words what's happening, and also be able to say, when I say something sounds bright, what does that mean? So, but this is in terms of this is what we call timbre. We're describing timbre. Timbre is the description of the sound. So, Sam, that sound, yeah, give me some more words. What else? Just give me some more words. Round, sharp, thickly bright. Yeah, fuzzy. So regarding this one right here. So let's talk about you're right. So, but let's talk about this one right here. It hurts my ears ish. Yeah. It's interesting that you say it hurts your it's interesting that you say it hurts your ears, because technically that's yeah, because sine waves are very unnatural. The sine waves don't occur very much in nature. So what we hear is complex waves. So if we move to this right here, so this one is a complex wave. So zoom in on it, and we have a triangle wave. So a triangle wave has a different wave shape. And let's give this one a listen for a second here. What changed?
It hurts more.
Yeah, hurts
There's
more.
Texture.
Yep, more texture, forceful. Yeah.
It's the sound like when you have your headphones like halfway plugged in.
Yeah. Before it gets all the way in. Yeah, when you're like plugging in like a cable. Fuzzier. Yeah, brighter. Yeah, High School Bell. Well, so that's interesting in terms of sound design. So if you want to make interface like computers, like maybe you're working on a film and you want to create maybe you're working on CSI or a sci-fi film, and they always have computers that always make sounds. Learning how to use these tones right here, not pure tones, but using tones to create interface, bleeps and bloops for computers is a great tool. You can really use this a lot. So, yeah, but to me, it sounds brighter. It's edgier. It's harsher. Watch your ears on this one. This one's going to be pretty bright. This one might be a little bit harsher. So now we're going to a square wave. Woo! Turn that one down a little bit.
Death now.
Yep. Oh yeah, that's sorry that you're listening pre-fader, so I'd have to gain this thing down. But we can see that it's much harsher right there. So and a square wave has much more like brightness to it. So if we go from in the case of what we just did, we just went from a sine wave, which is a pure tone, and then we went to these other ones that are non. So anything but a sine wave is going to be considered a complex tone. But let's listen to one of these ones right here. Let's listen to. I've got some bells here. I don't know what this one is, but let's go back to the top and listen to it. Where's my play button? Cool. Here's another bell, another kind of bell. And if we zoom in on these ones, for instance, let's just do a triangle. Let's do a bell. Let's move in on this bell right here. If we look at it closely, we see it's pretty chaotic looking right there. And that's because we have multiple different sounds happening at the same time. Multiple different harmonics is what we're going to say. But there's multiple different sounds. And so therefore, even though it's like to our eye right here, it's hard for us to see the repeating pattern of this thing right here. But the fact that we can hear a tone and that it's tonal says that it's going to be an actual, that it actually has something that's periodic. So I didn't really mention this before, but for something to have a tone, like a pitch to it, not a pitch, but have a tone, it has to be something that repeats itself over and over and over. And in this case, we can indeed hear that it's dinging. It is dinging over and over and over. So it's ringing out. So therefore that has tone implies that it actually has repeating sounds in here. But even though we can't see it, it's all over the place. So it doesn't look like a sine wave. So therefore it's what we would call a complex tone. Let's see. Yeah, let me try one more. Let me see. That was, sorry, it switched sample rates on me. Like my interface takes a second to switch sample rates. Why don't we call it for there? So I'm going to go ahead and hit stop here for a second. Like I said, we're gonna change the syllabus up a little bit. We're just gonna work on chapter 1 for the rest of this week right here. Sorry, Rowan, I couldn't see. I can't see you guys when I'm doing that. So, like, were you waving your hand with a question, or were you waving your hand just because you want to say what's up?
Oh no, because we were arguing over what the best wave was, so I said, "What about me waving my hand?"
Got
Sorry,
it.
that was a
Clever.
bad joke.
Cool. That's all good. All right. So, Britt, I'll get to you in just a second here. So what I'm going to do here is, and so by the way, if like, Britta, can you do me a quick favor? Can you do the reactions raise, or can you do the raise hand in the, like, raise your hand? I want to see like the tech, not your, but doing it in the thing. Where does that show up? I want to try and see where that shows up. Got it. Okay. So it shows up in the chat, not in the, on your thing, but I'm hoping it puts the people who are on page 2 to page 1. So we're done for the day today. So what I want you to do is get your clickers all set up, read through chapter 1, and then we're going to continue on with the discussion on chapter 1 for the rest of this week. And the first homeworks are due on Thursday night. And I'll stick around. This is my office hours, but I will answer any questions that we have coming up here. So, but I'm going to sign off on the recording and have a great rest of the day. See you, my friends.